Hello and welcome to this revision session on electric fields and capacitance, which is part of the AQA A-Level Physics course for paper 2. So in today's revision session we're going to look at how to answer examination questions on the topic of electrical fields and capacitance for AQA A-Level Physics. So if we've been successful and learned in today's revision session, we should be able to answer A-Level Physics examination style questions, assess your understanding on A-Level Physics, and then finally understand what topics you need to improve upon for A-Level Physics, especially in paper 2. So how do you prepare for this revision session? Well, when completing your work in this revision session, divide your piece of paper into two sections. Make the section on the left hand side larger than the right hand side, and in this left hand side section write down your work and answers to the question in the revision session. When you're doing this, make sure you write out the answers in full sentences and show your full working out. Whilst on the right hand side, write down any piece of information which you find useful, any hints and tips on answering questions from this revision session. And at the end of the revision session, write up these notes into a revision sheet for you to use independently. So how should you be revising AQA A-Level Physics? So the first step is to learn the key facts. Use the revision guides, the class workbooks, the prep notes and the textbooks to learn the key ideas of the course, and you may wish to make mind maps or write out notes yourself. The second step is to test yourself. Use Caboodle, Seneca, your knowledge checkers to quickly test your own knowledge, and you may wish to do this retrieval from your own cue cards. Then step 3, practice exam style questions. So either use the exam prep books, homework books, supervised study books, additional workbooks to answer exam questions and mark your own work, and you may wish to download your own exam past papers to do this. So your 3 steps of learn the key facts, testing yourself and practicing examination style questions will help you in your preparation for revising AQA A-Level Physics. So what part of the specification are we covering in today's revision session? Well, we're going to be looking at 3.7.3 electrical fields, which includes ideas on Coulomb's law, electric field strength, electric potential. We're then also going to look at 3.7.4 capacitance, which covers the definition of capacitance, parallel plate capacitors, energy stored by a capacitor, and finally capacitor charge and discharge. So let's have a look now at a few multiple choice questions on electrical fields and capacitance. So the force between 2-point charges is F when they are separated by a distance r. If the separation is increased to 3r, what is the force between the charges? So pause the video now, then unpause the video when you want to go through your answer. Right, the answer here is going to be D, because we should know that the electrical force equation, Coulomb's law, is given by Q1 Q2 over K R squared, where K is the constant, 1 over 4 pi epsilon 0. So this tells us that if R is increased to 3R, well therefore F is going to become F over 9, because we're dividing by R, but because it's R squared, 3R becomes 9R squared when it works it through, so therefore it's F is F over 9 now, so our answer is D. The next question says, the diagram shows 2 patterns of field lines X and Y around a particle. Which row is correct when the particle is a proton? So pause the video now, then unpause the video when you want to go through your answer. Right, our answer for this one is C, because electrical field lines show the direction a positive charge would take, and gravitational field lines show the direction a point mass would take. So because gravity is always an attractive force, the field lines should be pointing inwards, because the 2 massive objects will be attracted to each other. But for the electrical field lines, because the direction a positive charge would take, it should be pointed away from the proton, because positively charged particles will repel a proton, so therefore they'll be pointed away from it. So therefore the electrical field is going to be X, whilst the gravitational field is going to be Y. The next question says, 2-point charges of magnitude Q are separated by a distance r. The electrostatic force experienced by each charge is F. What force will be experienced by each of the 2-point charges of magnitude 3Q separated by a distance of 2r? So pause the video now, then unpause the video when you want to go through your answer. Right, our answer here is C, because like I said before, Coulomb's law says that F equals Q1 Q2 over K R squared, where K is 1 over 4 pi epsilon 0. So if R becomes 3R and each Q becomes 3Q, well therefore we can say F is equal to 3Q times by 3Q over K over 2 are all squared. So therefore 3 times by 3 is 9, 2 squared equals 4, so it's going to be 9f over 4. So our answer is C. The next question says, the diagram shows two parallel plates. They're conducting plates, and a graph of the variation of the potential between the two plates is shown. What is the magnitude of the electrical field strength between the plates? So pause the video now, then unpause the video when you want to go through your answer. Right, you should be aware that in a VR graph, okay, the gradient of the line is the electrical field strength. So when you're using our VR graph, we can work out our gradient because it's going to be the change in y, which is 800, 0 to 800, divided by the change in x, 0 to 0.02, because we're working centimeters, remember, we work in meters, sorry, and the graph is given in centimeters. So therefore it's 800 over 0.02, which is 40,000 newtons per coulomb. The next question says, the graph shows the variation in the electrical field strength E with a distance r from the centre of a charged body. What is the potential difference between a point where r equals 20 centimetres and a point where r equals 40 centimetres? So pause the video now, then unpause the video when you want to go through your answer. Right, our answer is going to be B, because you should be aware that in an ER graph, the area under the curve is the potential difference. Now, therefore, we've got to work out our area from 20 centimetres to 40 centimetres. So what you can do is work out the area underneath by splitting it up into a triangle and a square and a rectangle. So therefore, you can work it through by working out the area of the triangle between 20 and 40 and the square or rectangle between 20 and 40. But the trick you've got to remember is that the y-axis is kilovolts per meter, so you've got to convert those values from for example from 50 to 50,000 or from 150 to 150,000. So you work it through and you get 20,000 volts. B. The next question says, point P is a short distance from an isolated positron. What are the signs of the electrical potential and the gravitational potential at P? So pause the video now, then unpause the video when you want to go through your answer. Right, our answer is going to be B, because gravitational potential will have to be negative, because gravitational potential is always negative, because gravity is always attractive. Now, in this instance, the electrical potential will be a positive, as the electrical field is repulsive, because it's carried out in a field produced by a positive charge, and the positron is a positively charged particle, so therefore you'll get repulsion, which is indicated in potential with a positive value. So our answer is B. The next question says, a capacitor of capacitance 9 nanofarads has plates with overlapping areas of 18 centimeters squared separated by a dielectric of thickness 0.15 millimeters. What is the relative permittivity of the dielectric? So pause the video now, then unpause the video when you want to go through your answer. Right, so what you've got to do is you've firstly got to make relative permittivity the subject of the equation. Now the equation is given to you in your equation book, but it has capacitance as the subject. So you rearrange it and make relative permittivity ER the subject of your equation. So you say ER is equal to C times by D over A times by epsilon 0. Now epsilon 0 is given on the equation book, it's 8.85 times 10 to the minus 12. We know what C is, the capacitance, it's 9 times 10 to the minus 15, because we're working through as in nanofarads, and we know what the diameter is, the distance between the two objects is, it's going to be 0.15 times by 10 to the minus 3, because it says 0.15 millimeters, and we know what the area is, it's 18 times by 10 to the minus 4, because we need to be working in meters squared, and to convert from centimeters squared to meters squared is times 10 to the minus 4, because centimeters to meters is times 10 to the minus 2, and there's 2 of them, so it's 10 to the minus 2 and 10 to the minus 2, which is 10 to the minus 4. You can work that all the way through and you get your answer out to be 85, which is given to be 8.5 times 10 to the 1, which works it through to be A. The next question says, a capacitor of capacitance 10 microfarads is charged through a resistor R to a potential difference of 20 volts using the circuit shown. When the capacitor is fully charged, which of the following statements is incorrect? So pause the video now, then unpause the video when you want to go through your answer. Right, our answer here is going to be B, because if we work out the energy stored in the capacitor, we say E equals a half CV squared. So it's a half times by 10 to the minus 10 times 10 to the minus 6, because we're going from microfarads into farads, times by 20 squared, which is the potential difference. So we get 2 times 10 to the minus 3, which is 2 millijoules. So the energy stored by the capacitor in theory should be 2 millijoules. However, that's not the total energy stored, as some energy is wasted in the charging process, so therefore B is going to be incorrect. The next question says a voltage sensor and a data logger are used to record the discharge of a 10 millifarad capacitor in series with a 500 ohm resistor from an initial PD of 6 volts. The data logger is capable of recording 1000 readings in 10 seconds. After a time equal to the time constant of the discharge circuit, which of the rows gives the PD and the number of readings made? So pause the video now, then unpause the video when you want to go through your answer. Right, our answer here is going to be D, because firstly, after one time constant, V will be at 37% of its starting value. Now, its starting value is going to be its maximum, which is going to be the EMF of the source, which is 6 volts. So after one time constant, you do 0.37 times by 6, because that's 37% of 6, which is 2.2 volts. Now, the time constant is equal to RC, which again is given to you on your equation book. So it's R, which is 500, times by C, which is 10 times 10 to the minus 3, because we go from millifarads into farads, so therefore it's 5 seconds. So in 5 seconds there will have been 500 readings, because there's 1000 readings in 10 seconds, so in 5 seconds there's going to be 500 readings. So our answer is D. The next question says, the diagram shows two particles at a distance d apart. One particle has a charge plus q and the other has a charge of minus 2q. The two particles exert an electrostatic force of attraction F on each other. Each particle is then given an additional plus q, charge of plus q, and then their separation is increased to a distance of 2d. Which of the following gives the force that now acts between the two particles? So pause the video now, then unpause the video when you want to go through your answer. Right, our answer in this particular question is going to be A, because you know that F is equal to Q, say F is equal to KQ1, Q2 over R squared. Now again, K is just a constant, so we can just ignore them. So therefore we can say that F is equal to Q1, Q2 over 2R all squared. Now you might think, does the value of Q not change as each one has been given a value of plus a Q? Well, what's happened is we've gone from 1 being plus 1 to being plus 2 because I've added a charge, but a 1 going from minus 2 to minus 1, so actually it's still 2 times by 1, so the value of charge on the top stays the same, but our value of R has gone up by 2, but that's been squared because it's R squared, so therefore F is now going to be F over 4. Now the thing is though, now one has gone from plus 1 to plus 2, and the other's gone from minus 2 to minus 1. We've still got a positive and a negative charge, so they'll still attract each other, so therefore it's an attractive force of F over 4, which is A. Let's now have a look at a few longer questions on electrical fields and capacitance. The first question says, Figure 5 shows a parallel plate capacitor connected to a 3 kilovolt DC supply. The capacitor is made from two identical metal plates separated by 5 millimeters of air. Each plate measures 30 centimeters in length and 20 centimeters in width. Figure 6 shows a side view of the capacitor. Draw on Figure 6 the electrical field lines between the plates, then calculate the electrical field strength between the two plates. So pause the video now, then unpause the video when you want to go through your answer. Well, the first one, remember what we've got to be aware of is that when we're going through this question, you've got to know that the electrical field lines will always go from your value of the highest value to the lowest, the most negative value. So therefore you're going to have at least 4 straight vertical lines because it's a uniform field. Okay, and the arrows are pointing upwards. So you know this because you've got your negative value at the top and your positive value at the bottom there, so it's going to be going upwards. Now the next one, the electrical field strength, well, we know that electrical field strength by definition is V over D. That's just a fact. So therefore we've got our value of V, 3000. We've got our value of D, which is the separation, which is 5 times by 10 to the minus 3, so we work it through to be 6 times 10 to the 5. The next question says the magnitude of charge stored on each plate is Q. Show that the electrical field strength E can be expressed as E equals Q over epsilon 0 epsilon RA, where epsilon 0 is the relative permittivity, or say epsilon R is the relative permittivity of air, and A is the area of overlap of the plates. Then calculate Q when ER is equal to 1, then state the electrical properties of a dielectric material. So pause the video now, then unpause the video when you want to go through your answer. Right, how do you answer this particular question? Well, you've got to link a few equations together. The first equation is it's a parallel plate capacitor. So we can say C is equal to A times by E0 ER over D. That's an equation given to you in your equation book. But we also know that C is equal to Q over V, which is just the equation for capacitance. And then electrical field strength, E is equal to V over D. Once again, all these equations are given to you. So what you can do is therefore substitute Q over V into the top equation and therefore rearrange it and make the subject to be V over D, and then at that point substitute E in to work out your value, and therefore you can say E is equal to Q epsilon over epsilon 0 epsilon RA. The next question is legitimately just rearranging that previous equation to say Q equals E times by E0 ER times by A, then popping all the values in. Now you're given ER in the question, you know E0 is 8.85 times 10 to the minus 12, that's given to you in your equation book, and you know your value of A from your previous question, so therefore you can say the answer is 3.2 times 10 to the minus 7. Now the last two values are just facts. It's the properties of dielectric materials, that they are firstly an insulating material, but also they will contain polar molecules or can be easily polarized. The next question says, figure 2 shows a capacitor and a switch S connected to a parallel combination of two resistors R1 and R2. The initial potential difference across the capacitor is 5 volts and the initial charge in C on the capacitor is Q0. Figure 3 shows the variation of log Q over C with time after S is closed. Determine Q0. So pause the video now, then unpause the video when you want to go through your answer. Right, it's very important that you can use log graphs when trying to work out values with capacitors. Now it's important to note that you can work out Q0 from a log QT graph because we know that our y-intercept is equal to log Q0. So if you read off your graph, read off your y-intercept, and you'll see that log Q0 is equal to minus 7.4. So what you can then do is work backwards to work out Q0. So if log Q0 is equal to minus 7.4, well then Q0 is equal to E to the power of minus 7.4. So if Q0 is equal to E to the power of minus 7.4, you work it through to get 6.1 times 10 to the minus 4 coulombs. The next question says, figure 6 shows an isolated spherical oil drop carrying a charge of plus 6.4 times 10 to the minus 19 coulombs. Assume that the oil drop behaves as a charged conducting sphere. Firstly, draw electrical field lines onto figure 6 to show the electrical field around the oil drop. Then define absolute electrical potential at a point in an electrical field. Then an oil drop has a radius of 1.4 times 10 to the minus 6 meters. Calculate the absolute electrical potential at the surface of the oil drop. So pause the video now, then unpause the video when you want to go through your answer. Right, in this one it's very important you can show the electrical field lines around the oil drop. So because it's a spherical object, it'll produce a radial field. So you need 6 radial lines which are straight and evenly spaced out with the arrows going away from the center. Why is that? Because the arrows show the direction that a positively charged object would take in the field, and positively charged objects repel other positively charged objects, so the arrow should be pointing away from it. The next question asks you pretty much to define absolute electrical potential, and the definition is it's the work done in moving a unit charge from infinity to a place in the field. That's the definition of absolute electrical potential, which you should just learn. And then how to calculate the absolute electrical potential? Well, if you look in your equation book, you'll see that V is equal to Q over 4 pi epsilon 0 R. Now, you've got the value of Q. We know it's 6.4 times 10 to the minus 19 is given in the question. We know 4 pi epsilon 0 because we can work those out from our equation book. And we've got R as it's 5.8 times 10 to the minus 5. Okay, as you can see, it's given it to you in the question. So you can work it through like that, and then you get your answer to be 4.11 times 10 to the minus 3. And then that's your absolute electrical potential. The next question says, figure 7 shows the charged oil drop stationary in air in an electrical field between two parallel plates. The potential difference between the plates is going to be equal to V. So firstly, draw and label arrows on figure 7 to represent the force acting on the oil drop. Then the potential difference between the plates is now reversed so that the oil drop is attracted towards the lower plate. Explain why the initial velocity of the oil drop is approximately 20 meters per second squared. Then describe and explain the motion of the oil drop after the potential difference between the plates is reversed. So pause the video now, then unpause the video when you want to go through your answer. Right, it's important to note that the question says to you that the oil drop is stationary. So this tells us that the forces must be in equilibrium with each other. So the idea is that when you look at this particular diagram, you're going to have weight acting downwards. So you're going to have mg acting downwards, but then in the opposite direction, you're going to have the electrical force acting upwards, Fe. Now the next question, it indicates to us why is the initial acceleration of the oil drop approximately 20 meters per second squared. Well, that's because in the previous question we said that the two forces were in equilibrium and that the electrical force counteracted the weight of our actual oil drop. Now the acceleration due to gravity, which is linked into our weight for our oil drop, is going to be about 9.81 because it's on Earth. Now if we have, that tells us that the force produced by this acceleration must be equal to the electrical force produced because it's stationary in the air. Now if you reverse the potential difference, you reverse the direction of the electrical force. So therefore we've pretty much doubled the force acting downwards on our oil drop. So now the acceleration has gone from 9.81 meters per second to be double that, which is approximately 20 meters per second squared. Now it says then describe and explain the motion of the oil drop after the potential difference between the plates is reversed. So now there's going to be a resultant force acting downwards on the oil drop because originally the upwards electrical force is now acting downwards. So this tells us that the oil drop will accelerate downwards, but as it accelerates downwards, because it's moving through air, the air resistance produced as the oil drop goes down will increase because it's moving faster, so air resistance gets bigger until eventually we reach a terminal velocity between the air resistance acting against motion and the resultant force of weight and electrical force acting downwards. The next question says, figure 6 shows two charged water droplets A and B in a thundercloud. The radius of A is 66 micrometers and the radius of B is 35 micrometers. Each droplet has a charge of minus 1.2 times 10 to the minus 12 coulombs. Assume that the charge on A and the charge on B are concentrated at their centers. The distance between the centers of A and B is 1.5 millimeters. Calculate the electrostatic force between A and B, and then the movement of air in the cloud causes A and B to move together until they touch. Calculate the work done against the electrical force in moving A and B from the position shown in figure 6 to the position where they touch. So pause the video now, then unpause the video when you want to go through your answers. Right, so how do you answer this particular question? Well, in the first one, we're trying to work out the electrostatic force. So at this point, we know that the electrostatic force from Coulomb's law is equal to Q1 Q2 over 4 pi epsilon 0 R squared. Now we've got the charge Q1, we've got the charge Q2 from our question because it says to us that the charge of each droplet is minus 1.2 times 10 to the minus 12 coulombs. We've got our value for r squared because the distance from centre to centre is going to be 1.5 millimeters. So therefore we can say that the value of r is going to be 1.5 times 10 to the minus 3 to give our value through to be 5.8 times 10 to the minus 9 newtons. Now the next one is calculating the work done against the electrostatic force in moving A and B from the position shown to a position where they touch. So the point is we're trying to work out our change in potential, so we can work out our potential energy difference. So we can say that V is equal, our potential is Q over 4 pi epsilon 0 R. So what you can do is you can work out the potential at 1.5 millimeters for one charge, so you work that through and get your value in, okay, and then at that point you can then also work out the potential at 101 times 10 to the minus 6 meters for one of the charges, so you get it to be 107 volts. So what you can then do is you've got your potential difference, so you find the difference between the two values, so 107 minus 7.2, so therefore you get 100 volts, and then you can work out the potential energy difference due to this by doing the potential difference is therefore equal to the work done over the charge, so therefore work done is the potential difference times by the charge, so it's 100 volts times by the charge of the object, which is 1.2 times 10 to the minus 12, so we get 1.2 times 10 to the minus 10. So just to clarify, why do we get the potential at 1.5 millimeters and why at 101 times 10 to the minus 6 meters? Well, if you look through here you can see that that value is that when the difference is going to be 1.5 millimeters in that particular question, and then we're calculating the work done from that position to where they touch. So we're looking at the difference between the two of them. So when they're touching, the centers are different by about, so you can see, 66 micrometers and 35 micrometers from center to center at that point. So therefore you can work out what the distance is at that point, and that's the difference between the two of them. The next question says, figure 7 shows a simplified diagram of a thundercloud. The bottom of the thundercloud is negatively charged and the top is positively charged. Y is a point inside the thundercloud. EY is the electrical field strength at Y, so state the direction of EY, and then a charged water droplet is stationary at Y. The weight of the droplet and the force on it due to EY are equal in magnitude. The mass of the droplet is 1.38 times 10 to the minus 9 kilograms. The charge on the droplet is minus 2.1 times 10 to the minus 12 coulombs. Calculate EY. So pause the video now, then unpause the video when you want to go through your answer. Right, firstly, what's our direction of EY? Well, again, the electrical field will always point in the direction from positive to negative because it shows the direction a positive charge will move in. So therefore, it's going to be vertically downwards from the positive charge down to the negative charge at the bottom of the thundercloud, because once again, the direction of the field lines is the direction a positive charge would take. Now, to work out EY, how can we work this through? Well, it says that our water droplet is stationary. So we can say that the electrical force acting upwards is equal to the weight of the water droplet acting downwards. So we can say that our electrical force is equal to EQ. Our weight is equal to mg. We're given m in the question to be 1.38 times 10 to the minus 9. So you can work out our weight to be 1.35 times 10 to the minus 8. We can make that equivalent to EQ, and therefore we can say E is going to be this 1.35 times 10 to the minus 8 over the charge of the droplet in the water cloud, and we get 6.4 times 10 to the 3 volts per meter. The next question says, the base of the thundercloud and the ground beneath it can be modelled as two plates of a parallel plate capacitor with air between them as shown. The base of the cloud is circular with a diameter of 2.75 kilometers. The base of the cloud is 340 meters above the ground. Show that the capacitance of the capacitor is about 1.5 times 10 to the minus 7 farads, and that the capacitor discharges when the lightning strikes the ground. The charge stored in the capacitor before it discharges is 87 coulombs. Calculate the energy available for the lightning strikes. So pause the video now, then unpause the video when you want to go through your answer. Right, in this first one, we're going to have to use our equation for parallel plate capacitors, which is C is equal to A times by E0 times by ER over D. Now, you're given the value of D from the question is 340 meters, the distance between the two plates. Now, you've been given our diameter for the cloud to be 2.75 kilometers. So therefore, because it's a circle, you can therefore work out the area by halving your diameter to get your radius, but always work in meters. So convert your your kilometers into meters, and therefore you can work out your area to be pi r squared, and you get 5.9 times 10 to the 6 meters squared. You've got your value of E0 and you've got your value of ER from the questions. Okay, so what you can therefore do is pop them in to get 1.55 times 10 to the minus 7 farads. Remember, E0 is going to be 8.85 times 10 to the minus 12, and ER is going to be the relative permittivity of air, which is going to be 1. Now the next question asks you to work out the energy. Now you've got charge, and you've got the idea of your you've got your charge there, and you've got your capacitance as well. So you can use your equation E is equal to a half Q squared over C. Now you can pop in your values. You've got your charge from the question. You've just worked out capacitance, so you can work out your energy to be 2.4 times 10 to the 10 joules. Look to see what values you've been given in the question and refer to your equations, which are given to you in your equation book. The next question says, figure 6 shows a circuit used to transfer energy to a lamp in a camera flash. A battery of EMF 12 volts and negligible internal resistance charges the capacitor when the switch is in a position S1. The capacitor discharges through the lamp when the switch is in position S2. Assume that the capacitor is discharged completely after each use. The capacitor has a capacitance of 0.85 millifarads, so that the energy stored in the capacitor when it's fully charged is approximately 0.06 joules. The lamp emits a flash of visible light when the voltage across it is greater than the minimum voltage V min. The duration of the flash is 55 milliseconds. Assume that the resistance of the lamp is constant and has a value of 31 ohms. Calculate V min. So pause the video now, then unpause the video when you want to go through your answer. Right, in this first question, you're working out energy, but you've been given capacitance in the question, and you know what V is. It's 12 from the information given in the question. So we say E equals a half CV squared, so you get 6.1 times 10 to the minus 2. Remember to convert millifarads into farads by times and by 10 to the minus 3. Now in this next question, you're trying to work out V min. Now it's the idea of a capacitor, which is going to be discharging. So we can say that V is equal to V0 e to the minus t over RC. So what you can do is you've got all your values through, because you know what V0 is. It's going to be 12 there. So you know what R is. You got C in the question because you're given the value of R and you're given the value of C from your previous one. And then you know we can work it all through and you get 1.5 volts. Now the next question says the charging circuit includes a resistor and a 12 volt battery. The battery transfers a total energy of 50 milliwatt hours during its lifetime. Explain why only half of this energy can be transferred to the capacitor, and then calculate the maximum number of times the battery can charge the capacitor during the battery's lifetime. So pause the video now, then unpause the video when you want to go through your answer. Right, so the idea is that the energy is dissipated in the resistor in the charging circuit. So what you can therefore say is E is equal to a half CV squared, and so therefore what you can therefore do is then if you can work out the energy that's dissipated as it goes into the circuit and then how much is dissipated in the resistor, and you'll see that half of the energy is dissipated in the resistor as it's charging up. Now the next one is calculate the number of times the battery can charge the capacitor during the battery's lifetime. So the first thing you've got to do is you've been given an energy but you've not been given it in joules. So you're going to have to convert 50 milliwatts hours into joules. So you do that correctly, you get about 180 joules. Now to convert from milliwatt, so if you think about the unit is that energy is power times by time. Well, your power is being given in milliwatts and your time is being given in hours. Now joules is going to be when your power is given in watts and your time is given in seconds. So to go convert from milliwatt hours into joules, you multiply by 10 to the minus 3 to turn milliwatts into watts, and then you will also multiply by 3600 to convert your hours into seconds. So therefore that works out to be 180 joules. Now remember, it's half of that because half of it you've said has been dissipated out of the circuit when it's charging up, so you've only actually got 90 joules. And then we know that each charging process is going to be, discharging process is 0.06 joules from the previous question, so we get about 1500. The next question says the capacitor is then replaced with one of much greater capacitance. Explain how the replacement capacitor affects the duration and brightness of each flash. Then explain how the replacement capacitor affects the number of flashes the battery can deliver, assuming that the capacitor discharges completely each time the flash is used. So pause the video now, then unpause the video when you want to go through your answer. Right, so the idea is, how will the replacement capacitor affect the duration and brightness of each flash? Well, the idea is you've got a much greater capacitance, so therefore you've got a greater duration, or the brightness will decrease more gradually because you've got a greater time constant, so therefore it'll take a longer time to charge and also a longer time to discharge as well. So whilst the initial brightness is going to be the same, it's going to be brighter for longer, because whilst your initial value of charge you're going to have in your capacitor is the same, okay, the time it takes to discharge is going to be longer, so therefore it'll be brighter for longer. The next question says, explain how it will affect the number of flashes the battery can deliver. Well, there's going to be fewer flashes to be delivered because the energy stored in the capacitor is greater, because you know E is equal to a half CV squared, so we know that C has increased, therefore E has increased, so therefore it'll take, the fewer flashes will be delivered each time, so therefore the energy stored is greater, so therefore there'll be fewer of them delivered each one. The next question says, define the electrical field strength at a point in an electrical field. And then figure 2 shows a point charge of plus 46 microcoulombs placed 120 millimeters from a point charge Q. Position P is on the line joining the charge at a distance 66 millimeters from charge Q. The resulting electrical field strength at position P is 0. Calculate charge Q. So pause the video now, then unpause the video when you want to go through your answer. Right, the first one is just the definition of electrical field strength. So the definition is, it is the force per unit charge on a positive charge in the field. So the electrical field strength is the force per unit charge on a positive unit charge. Now, how do you work out the charge, calculate the charge here? Well, you'll notice that there are two charges. There's Q, and then there's the second one, which is going to be 46 microcoulombs, and you'll notice that at the resultant at P is going to be 0, so we can equate the electrical field strength from the left hand side and equal to the right hand side and work out your value. So what you can say is, you can say 46 times 10 to the minus 6 over 4 pi epsilon 0 0.054 squared, which is the distance from that charge on the right hand side to P, is equal to Q over 4 pi epsilon 0 0.066 squared, because again that's the distance from the charge on the left hand side to P. You can then rearrange it all, make Q the subject, and you get Q to be 6.9 times 10 to the minus 5, or 68.7 microcoulombs. And that also makes sense because you'll notice that the two are going to cancel out, and you notice that the 46 microcoulomb charge is actually going to be slightly closer. So therefore that tells us that the charge on Q is going to be slightly bigger to negate the fact it's slightly further away, to give equal electrical field strengths, so they cancel each other out at P. The next question says, a small rubber ball coated with a conductant paint carries a positive charge. The ball is suspended in equilibrium from a vertical wall by an uncharged non-conducting thread of negligible mass. The wall is positively charged and produces a horizontal uniform electrical field perpendicular to the wall along the whole of its length. Figure 3 shows that the thread makes an angle of 30 degrees to the wall. The thread breaks. Explain the motion of the ball. So pause the video now, then unpause the video when you want to go through your answer. Right, so what's going to happen is that you'll notice that when the thread breaks, there's going to be two forces acting on the ball, because you've got a charged ball, okay, and it indicates it's got a positive charge, so it's going to follow the electrical field lines in the horizontal, so the ball is going to accelerate horizontally to the right hand side, but because it's now falling, it will accelerate down vertically downwards due to the force of weight. So therefore we've got our electrical force accelerating to the right, and our weight force accelerating it vertically downwards. So therefore you're going to have acceleration in a straight line at 30 degrees to the vertical away from the wall, because you're going to have two accelerations act on the object, one in the horizontal due to the electrical field, and one in the vertical due to the gravitational field. Right, so I hope you've enjoyed this particular revision session where we've looked at answering A-level physics examination style questions on electrical fields and capacitors. So hopefully you feel you can answer those A-level physics examination style questions, you can assess your understanding on A-level physics, and finally understand what topics you need to improve upon for this particular topic. So thank you very much for watching this revision session on electrical fields and capacitance for AQA A-level physics on a paper 2 topic. Thank you very
very much for watching and have a lovely day.